Good afternoon, everyone. I'm Yumu. It's my honor to introduce Professor Jeffrey Johnson to you. Dr. Johnson was born in Emporia, Kansas, and earned his bachelor degree at the University of Kansas in 1994, graduating with highest distinction and honors in chemistry. Then, Dr. Johnson performed graduate research as an NSF graduate fellow in the laboratories of Professor David Evans at the University of at Harvard University from 1994 to 1999. After receiving his PhD degree in 1999, Dr. Johnson was an NIH postdoctoral fellow in the laboratories of Professor Robert Bergman at the University of California at Berkeley. In 2001, Dr. Johnson joined the faculty at the University of North Carolina at Chapel Hill. Since 2014, Professor Johnson is a Ronald Gallant Distinguished Professor in the Department of Chemistry. Professor Johnson's research interests lie in the general area of chemical synthesis. They are particularly interested in the discovery of new organic transformations and their application to the total synthesis of architecturally challenging and biologically important natural products. Today, Professor Jeffrey Johnson would like to give us a presentation on stereoconvergent and stereodivergent synthesis with configurationally unstable compounds. Let's focus on Professor Jeffrey Johnson again and enjoy his talk.
Okay, thank you for that very nice introduction. I really appreciate it, and I'm grateful for the opportunity to come and give this webinar to your center and share a little bit of what my laboratory is interested in and kind of maybe a little bit about how we go about problems. I'm in this, as many of you are familiar, I'm in this Zoom land where I'm seeing only my screen, and so I'm sort of in sensory deprivation. So if anything is going awry, just send me a message or speak up on the microphone or the chat. I'll also say that I'm speaking to you from the visiting faculty housing in Bilbao, Spain, which is very nice, but it happens to be co-located in an undergraduate dormitory. And so for once in the pandemic, if you hear screaming in the background, it's not my daughters, it's undergraduates, Basque undergraduates who are probably coming back from dinner. So I apologize if there's any background noise, but that's the source. Let me slide advance here, maybe. Okay, so before I just dive into the topic for today, I thought I would just very briefly give an overview of some of the things that I won't be talking about, but some of the things that are important to us as a research group. I would say broadly what drives questions we like to ask in my lab are questions around interesting chemical reactivity and interesting structure. And so molecular complexity in the form of bioactive natural products can be inspirations to us to try to develop new methodologies. And so I'm using a laser pointer. If it's not appearing, someone speak up or send me a message, but if it's okay, no need to say anything. So on the bottom half of the slide are illustrations of two complex alkaloid natural products that are of interest to us from the standpoint of interesting biology, but from our perspective, the driver for a lot of our interest is in development of new chemistry. And what you'll see in both of these sort of cartoon representations or cartoon breakdowns is that we're interested in using benzene rings as precursors to complex cyclohexanes. So dearomatization is a type of reaction that interests us a great deal. You can see the same thing in our approach to a molecule like tetrodotoxin, where this complex cyclohexane here, we propose to originate from a much simpler aromatic precursor in the form of this phenol. What I'd like to focus on today is what's in the upper left corner of the slide, which is just a simple cartoon representation of our approach to many problems in stereoselective catalysis, which is how does one convert prochiral pi bonds that have pre-installed chirality associated with them. So an asymmetric center that exists in a molecule that's a racemic mixture, how does one gain access to single isomeric products? And so that's what I'll focus on today. So I know this is a very diverse audience, and so I think in those situations, it's good to have sort of one take-home message that can span multiple disciplines, and this slide is my take-home message to span all disciplines, which is that stereoconvergent synthesis or stereoconvergent catalysis is simply an embodiment of Le Chatelier's principle. So what happens in stereoconvergent catalysis is one tries to establish an equilibrium between two enantiomers of a starting material, and there must be an obligatory achiral intermediate through which those enantiomeric forms pass in order to have this sort of equilibrating system. So as you know, if you perturb a system from equilibrium, the system will act to restore that equilibrium. And so the way that the equilibrium is perturbed in a stereoconvergent synthesis is to withdraw one component, in this case, one enantiomer, through the action of a catalyst that converts it to a new product. And that reagent, if you will, is replenished by the pre-existing equilibrium. So we can recognize this as its archetype, which is the Noyori dynamic kinetic resolution of beta ketoesters, which is done on hectoton scale annually and was part of the work that resulted in him receiving the 2001 or co-receiving the 2001 Nobel Prize. So in this cartoon sense, the orange ball would be an ester, and thus this equilibrium is facilitated by the very high thermodynamic and kinetic acidity of this red proton here, which is easily lost to the enol or enolate and then reformed unselectively. So these are, in the Noyori case, these are hydrogenation reactions where H2 is used as the stoichiometric reductant and one forms chiral secondary alcohols that install two asymmetric centers. If you're interested in more on this topic, there's many reviews that have been written on it, but this is one of the more recent ones from ChemRev in 2017. So what I will say is that we kind of got into this area in a way that's common to a lot of the areas we've gotten into, which is by accident. And it spawned from some discussions we had about 10 or 11 years ago in lab meetings about a synthetic problem in natural product. But what it led to is a recognition that this sort of process is actually unknown for alpha ketoesters. So in this case, where the green ball is an ester, these types of reactions were not known, despite the fact that if you imagine adding, for example, say hydride here, this would lead to glycolic acid derivatives, that is alpha hydroxy acid derivatives, which could be of high value in terms of building blocks, particularly if one was able to control what's going on out here. So that was the genesis of a lot of chemistry that, as I said, was developed at the start about 10 years ago by an extremely talented graduate student named Kim Stewart and an UNC undergraduate named Emily Gentry, who is just beginning this summer a new faculty position at Virginia Tech. So what they found is that you ignore, for the time being, if you ignore the left-hand part of this molecule and just focus in on this part here, here's the alpha keto ester. The only thing that's really happening in this reaction is we're adding a hydride to the ketone. The hydride is being delivered by formic acid as the H2 equivalent. So this is a transfer hydrogenation. It's being mediated by what I'll call the second generation Noyori catalyst, which is this chiral catalyst that I'm showing here. So in addition, what happens in this particular compound is we have two ester groups. And so the initially formed hydroxyl group actually cyclizes onto one of these two groups, which happen to be diastereotopic. And so one actually gets a third stereocenter in the product. And so the good news is that we were able to do that with good diastereo selectivity, but you can see that the recognition of the two enantiomeric starting materials was relatively poor. Now, the next experiment was definitely not this one. This is probably the 100th experiment, but what Kim did was to basically build out a new variant of the Noyori catalyst that then was extremely selective for recognizing alpha keto esters in particular, and in this particular system worked extremely well to give nice enantiomer selectivity for these gamma butyrolactones. These gamma butyrolactones are present in about 5% of all naturally occurring substances, as it turns out. So this is a sort of a complementary way of putting these together relative to what had been previously reported. I wanted, because of this center's interest, I wanted to take a little bit of a side trip to talk a little bit about how we made the starting materials to do this reaction. And actually, although the functional groups looked a little bit arbitrary as I presented them, they were all put there for a reason. So these are the products that we're making. It turns out they're extremely simple to put together. So what we do is we do a condensation reaction between a commercial malonate and whatever aldehyde you happen to want to use. That's a reaction that's catalyzed by an ammonium acetate, and it gives water as the stoichiometric byproduct to give this alkene. We then do a hydroacylation reaction. So we add this CH bond across this very electrophilic olefin, and that's catalyzed by an N-heterocyclic carbene. And all of the stoichiometric molecule, all the atoms from the stoichiometric reagents end up in the product. So this is a 100% atom economic reaction. And so this is the substrate that we use to then do the Noyori reaction, which uses formic acid as the delivery reagent for H2. So that spits out carbon dioxide. The cyclization spits out methanol. So the sum stoichiometric byproducts of this three-step process are water, methanol, and CO2. And the stoichiometric inputs are aldehyde, malonate, glyoxylate, and formic acid. And so you're getting a reasonably complex and stereodefined product from three catalytic reactions that have minimal byproducts associated with them. I say quasi-green here in the title because, of course, we're neglecting a mass intensity that comes in the form of solvent and other processing such as chromatography. But nonetheless, at least thinking along these lines, I think is useful from the perspective of trying to design green sequences or thinking about sustainability. And we try to apply that where we can in our synthetic work. So this is summarizing many person years of work in terms of this general cartoon here. The good news is that what Kim developed turned out to be applicable to a pretty broad range of alpha ketoesters, regardless of what the orange and the blue balls are, as well as phosphorus containing groups here. So when this is a phosphonate, alpha ketophosphonate, these sorts of reactions also work quite well. So the thing that we try to do in my lab is to identify common mechanistic paradigms or types of reactions that can provide product diversity from a similar mechanistic platform. And so if you looked at these molecules independently, you might not be immediately gravitating to them originating from a single type of reaction. But in fact, all of the compounds that I'm showing on this slide here are originating from this cartoon right here. So the good news is that one can generate a fair bit of product diversity essentially from doing the same reaction on different types of starting materials. Now that came from a fair bit of good fortune by the fact that this catalyst or this variant of the Noyori catalyst turned out to work extremely well for a wide range of compounds. Now all of these are reductions, and so that is necessarily giving one a secondary alcohol as the product. And so the next question that we asked was, can one increase the level of complexity in the products and generate tertiary alcohols if the incipient nucleophile is, instead of a hydride, is a carbon nucleophile? So this, of course, is a cartoon, but we want to ask the question, is there a way that we can catalytically generate carbon nucleophiles that will selectively recognize one enantiomeric form of the starting material over the other? So again, appreciating that there's varying levels of, or varying expertise in the audience, I don't want to get too bogged down, at least in the presentation, on the details. I'd be happy to certainly spend as much time as anyone wants in the Q&A on some of the details, but suffice it to say that if you can have a system where you use a base to generate a carbon nucleophile, and that same base can do acid-base chemistry on the starting material, and that's of course obligatory in order to racemize the starting material and set up the racemization equilibrium that's required in order to have a stereoconvergent process, then you can generate various products of this type. And so that's what's summarized in these publications here. And around the periphery of this slide, I'll just illustrate that we can add aldehydes as a nucleophile. So we do polarity reversal catalysis here, where we basically invert the polarity of this carbon from minus to plus, and then that acts as a nucleophile to make this bond here. This is a catalyst. I need to emphasize across the board that we're taking information from the literature and we're taking catalysts from the literature and applying them in new contexts, but we're definitely taking advantage in this case of chemistry developed by Rovis and Bodie. In this case, we're taking advantage of chemistry developed by Glorious and Bodie for carbenes engaging unsaturated aldehydes. Now, in this case, this carbon becomes nucleophilic, and we're making this bond here. So similar mechanistic paradigm, but completely different product types that one sees. We can do simple additions of alkynes using Carrera's, a modification of Carrera's conditions. So we're essentially generating an anion at this position, and it's doing a nucleophilic addition to give us products of this type under zinc catalysis. And then here we're taking advantage of very nice chemistry developed by Hayashi and Miura to essentially generate aryl rhodium nucleophiles using chiral complexes of this type. And so again, if you scan just very quickly the periphery of this slide, these compounds again don't jump out at you as being especially linked to one another until you kind of focus in on this tertiary glycolate type of subunit. That is an alcohol next to a carboxylic acid derivative. And so we can unzip them, all of these, or unpack all of these basically to a common mechanistic paradigm. So I think that I want to transition now. Everything that I've presented to this point is chemistry where we're doing pi bond additions, where the pi bond is a CO pi bond. So it's a carbonyl electrophile. We're making alcohols as the products. And that's facilitated again by the interconversion of the enantiomeric forms of the starting material through an achiral intermediate. Now, in principle, one can do a similar type of operation with an electrophilic pi bond. So we can recognize this conjugated system as being susceptible toward nucleophilic attack at this carbon. And we can also recognize this proton as being more acidic than a normal proton by virtue of the fact that it is potentially participating in this conjugated system. Again, in this case, it would generate an achiral intermediate and thus constitute a potential mechanism to interconvert enantiomeric forms of the starting material. So relative to, say, Noyori type reactions, this was a relatively underdeveloped method for which we could only find 2 examples at the outset. So again, considering the interests of this CCI, I wanted to show this chemistry because again, it focuses on an element of sustainability that I think is important. So the starting material that we chose to examine is called alpha angelica lactone, which is this compound in the middle here. It's a nice reagent for synthetic chemistry because of its lignose cellulose origins, and so it originates from a renewable source. It itself, you will of course recognize as being achiral, and this is the more thermodynamically stable form of angelica lactone, but there's also a beta angelica lactone, which is a constitutional isomer that moves the olefin from this position into this position. So when you convert alpha angelica lactone to beta angelica lactone, you generate a chiral molecule, and there's no selectivity in that isomerization in the absence of a chiral reagent. And so what we wanted to do was use angelica lactone as a reagent, unselectively migrate the olefin into conjugation. That migration then renders this olefin electrophilic here instead of nucleophilic as it is here. And so that might be susceptible to reactions with nucleophilic reagents. Now, angelica lactone, everything else I'm showing on this slide is mechanistically both feasible and established. So in the presence of water, angelica lactone will revert to levulinic acid. And so levulinic acid can be the precursor to angelica lactone by dehydration, of course. Angelica lactone is known to dimerize under certain conditions to give angelica lactone dimers. And it's also known that it can polymerize to give polyangelica lactone. So all of these red rate constants, if you will, need to be managed in order to have a stereoconvergent process that leads to lactone products that stereoconvergently result from alkylation. So this was part of the PhD thesis of Jess Griswold. And again, I'm going to do her a bit of a disservice and a lot of hard work that she did by skipping straight to the punchline, which is that, first of all, she observed all of those, most of those competing rate constants that I alluded to, but figured out really clever ways to manage them. And so what's really critical in this process is having this cocktail of organic base and inorganic base. And so we're again using the Hayashi-Miura chemistry to activate boronic acids as the nucleophile in the presence of a rhodium catalyst. And these are the catalysts among which Jess was using. The inorganic base is required to activate the boronic acid. So you see that we have some variation here in terms of the inorganic base that we're using. Then we've got an organic base in there as well. The organic base is the reagent that helps isomerize alpha angelica lactone into beta angelica lactone, which is the form that we need it. And you'll notice that the best results that we get are when we make the base as small as possible. So this is an important point about stereoconvergent catalysis in general, is the decoupling of thermodynamics and kinetics. So in this case, NMP and triethylamine have essentially identical PKBs thermodynamically, but they behave very differently kinetically because of their size. So in this case, Jess needed to use NMP in order to establish the most rapid equilibration of angelica lactone into and racemization of the beta form. So with all of those sort of stars aligned, right catalyst, right inorganic activator, and right organic base, we can get good enantiomer selectivity and good product ratios here. So this slide is just to say that under the optimized conditions, we can do a nice job of converting not only angelica lactone, but a variety of these unsaturated lactones into their derived beta alkylated products. And this further exemplifies some of the scope just with angelica lactone itself. So I am going to, I think, wrap up with just one slide that was, or one experiment that was sort of surprising to me. Maybe it's not to you, but you know, for this reaction to work, as I said, this olefin needs to migrate into conjugation here. And Jessica used a solvent system that's pretty common in these types of alkylation reactions, which is a dioxane water mixture. And so when I sort of naively expected that when you exchange water for D2O, that you would get 100% deuterium incorporation at all of the exchangeable sites. And in fact, she does see deuterium exchange, but only partially. And so this is the putative intermediate that one would generate from a reaction of N-methyl pyrrolidine with angelica lactone. And so what this says to us is that at least part of the racemization mechanism, this intermediate this ammonium salt redelivers the proton without ever giving D2O a chance to compete for that redelivery. So that is a mechanism by which one could still racemize the starry material, but not incorporate deuterium into the product. So that's not super important from a practical perspective, but it's a little, we try to really think hard about how these reactions are working. And this is one example of an experiment that Jess did to make some insight there. So it is 10 o'clock my time, and half an hour was what was suggested. So I am going to make the executive decision to cut off the stereodivergent part of the talk. I would obviously be happy to discuss any aspect of that chemistry. It has been recently published, and so if you're interested in that and feel shortchanged by me not covering it, first of all, I apologize, but second of all, I'll provide the reference here in a moment. This is the reference. And I will just want to conclude by thanking a really fantastic team of students who are the intellectual and experimental drivers of the science. I've necessarily covered many years of science here to kind of give you an overview of this particular aspect of our program. But we're I would say we're evolving into version 2.0 or 3.0 or 4.0 of stereoconvergent chemistry. And every time that I think that we're done with this area, I keep getting surprised. And it's a credit to the students that they keep surprising me as we peel this orange. So there I will stop, and maybe I'll stop sharing screen, and of course be happy to answer any questions.
Thanks for Professor Jeffrey Johnson's great talk. Students and postdocs could ask questions firstly. Luca, please.
Hi, Professor Johnson. Thank you. This is a lot of fun. Thank you for the seminar. For the Angelica lactone work, if you start from the alpha, beta unsaturated lactones, either racemic or either, do you get the same result?
Yeah, great question. You get very similar results. So it turns out that so we tried to stoichiometrically generate the equilibrate alpha angelica lactone to the beta form as the starting material, and the equilibrium favors the alpha angelica. I don't totally understand the nomenclature for alpha angelica lactone, but the alpha form is it's conjugated to the enol ether. Okay. So if you do start with that mixture, you do get very similar results. And so it doesn't really matter if you're starting from the alpha or the beta, which is good news, because that means you can go in with a mixture if the synthesis happened to give a mixture of the conjugated with the as the enol or conjugated with the carbonyl. Yeah,
cool, thanks. Question. Yeah, that makes a lot of sense based on the mechanism. Yeah, but thanks.
Yeah, thanks for the question. I appreciate it.
Any questions from postdocs or students? Okay, if there's no questions from students and postdocs, faculties, please feel free to ask questions. Hi, Alex.
Hey, Jeff, nice talk. I was curious, you showed some transfer hydrogenations with formic acid as the hydrogen source. Are there other hydrogen sources you've looked at, either for transfer hydrogenation, or can those run with hydrogen also? And are there any complexities that are added with different hydrogen sources?
Yeah, great question. So the original system was reported with isopropanol, and those do exhibit some reversibility, and so you can at least, well, I doubt they would be reversible with the systems that we're using, but with the aryl ketones to benzoic alcohols, Noyori did see some reversibility at high conversions, and so you would start to see erosion of enantioselectivity selectivity at high conversion. So the formic acid is nice because it just drives it by loss of CO2. There is a pretty specific system that he subsequently developed that could use hydrogen. It was very different, and it would probably not be compatible with the conditions that we need in order to get racemization to occur. So I think it ended up being maybe a ruthenium triflate, so in that case he could run it as a hydrogenation rather than a transfer hydrogenation. We didn't spend a lot of time looking at that, just because for those of you that may be thinking about using these reactions in your own research, I highly recommend them. They're phenomenal reactions. The catalysts are great. They're very clean, and formic acid is obviously super convenient to deal with. And so, yeah, for that reason, we probably didn't spend a ton of time looking for H2 based reactions. That was a long answer to, that was probably more than you wanted, but.
No, it's really helpful. I wouldn't have thought about the reversibility with isopropanol. That's a neat aspect.
Yeah.
Any questions from faculty?
I have a question. This is super general, but
Sure.
I heard in your introduction that you did work with Bob Bergman.
Yes.
But from your talk, it seems that, I don't know, maybe I'm mistaken, you don't really do catalyst development. It's not a, it's just a curiosity. Kind of like, how do you approach it? Because you also mentioned some conditions developed by others. And I think, yeah, that might be useful for me and students to know a little bit more.
Yeah, great question. So I am sort of a pragmatist when it comes to, I sort of gravitate toward the tool that will help me and my team to achieve the reaction that we're interested in. So I think it's probably accurate to say we don't do anymore. We don't do a ton of catalyst development, at least we haven't been. I think, you know, if I take the initial case that I showed, the transfer hydrogenation reaction, what we did there was, so the ligand that Kim developed, no one had made before. And so that was a reaction that sort of the basic platform was in place, but it wasn't selective in the way that we needed it to be. And so, so Kim was able to essentially rework the ligand framework in order to get in that case, the reactivity was fine. And so we didn't need to do any catalyst work in terms of getting the reaction to go. It was more on the selectivity side. So yeah, maybe a good way to answer your question is also that it's a question of which problems to tackle. And so we're often going for the reaction that we want to do and figuring out if there's a catalyst that can essentially do the type of transformation we want, and we use that at least as a starting point.
Yeah, again, it's not a criticism. I actually think people develop their own, they do catalyst development because they don't want to keep up with the literature. So, well, that's one way to put it. But yeah, I think you need to be much more on top of current literature, right? Like when you work towards a specific problem. So.
Yeah, I think the place where catalyst development is really critical is when is when there's a gap, a gap in terms of what can be achieved with the extant catalysts.
Yeah,
in my opinion.
Yeah, well, and I also think some people really are better at catalyst design and ligand design, and then I just I was curious because I think yeah, how I will kind of want to see how you feel about your postdoc routes or.
Oh, well, that was I mean, that experience was invaluable. And the system that I worked on with Bob was basically, I mean, we've sort of found a new hydroamination catalyst by accident because we took dimethyl titanosine and studied what happened to it when you cooked it up with an amine. And it turns out the amine protonates off one of the cyclopentadienyl groups, and it gives you a we did accidental catalyst discovery
development,
in that
yeah.
case.
Yep, thank you.
But I mean, that experience was valuable because Bob was like, what's going on here? What's this little thing in the spectrum? And let's figure this out, and let's do the kinetics. And so, yeah.
Any questions from audience? All right, if there is no questions, let's thank Professor Jeffrey Johnson again, and thank everyone for participating in the webinar. Professor Jeffrey Johnson and the members at CSE, please stay here for our next session. Others, please feel free to leave.
Thanks, everyone.
Yeah, thank you for a nice seminar.
Appreciate it.